Her name was Denny. She walked the earth roughly 90,000 years ago, deep in the Altai mountains of Siberia. But Denny was hiding a secret, one that could shatter our understanding of history. Her father, a Denisovan, her mother, a Neanderthal. Denny wasn't just a fossil, she was a first-generation hybrid. And her very existence creates a paradox. If these two distinct human groups could meet, mate, and produce a daughter like Denny, are they actually separate species? Or have we been wrong about human boundaries all along?
This is What Is It? Uncovering the Unknown.
A quick note before we dive in. We are testing a hypothesis that traditional labels for human groups are incomplete. We are using genetic markers to map ancestry and migration, not to make declarations of absolute certainty. We will weigh the evidence, and we will flag what is solid and what is still uncertain. So what makes a species a species? The rulebook says reproductive isolation. One definition says that two populations are the same species only if they interbreed and produce fertile offspring. Take the mule. A horse and a donkey can mate, but the mule is infertile. That is nature putting up a stop sign. It shows that horses and donkeys are separate. Let's talk about big cats. It depends on who the father is. If a male tiger mates with a female lion, you get a tigon. Rare, and often closer in size to their parents. But flip the parent. A male lion and a female tiger. Now you get a liger. And ligers can grow massive because of how growth signals are expressed in hybrids. Some have reached well over 400 kilograms. That is double the weight of a typical adult African lion. But there is a catch. These hybrids are generally infertile. They are genetic dead ends. Biology still draws a line. Lions and tigers remain distinct biological species. Now bring this back to us. In the context of evolution, some regard Homo erectus as a different species. But Neanderthals and Denisovans, that is a different story. They interbred with early modern humans. And unlike the liger, they produced fertile descendants. Descendants that exist in our modern genetic code. This genetic compatibility suggests they belong to the same species, Homo sapiens, just early human populations who left Africa long before recorded history. We know this because of the Siberian Denisova cave. The first identification of a Denisovan did not come from a skull. It came from a juvenile finger bone, excavated in 2008. Nuclear DNA from this fragment showed close ties to Neanderthals. Neanderthals also inhabited that cave at various times. Look closely. The discovery of Denny confirms that a first-generation hybrid existed, found in the Altai Mountains. Genetic analysis revealed a Denisovan father and a Neanderthal mother. Researchers suggest that such interbreeding events were likely common in that region. This points toward a shared biological identity. They were not merely distant cousins. They were part of a single, interbreeding human family. Now, a skeptic would argue that this classification is not so simple. There are potential indicators of hybrid incompatibility, specifically in the X chromosome. If true, these indicators could justify a species distinction between these groups. The crux of the issue lies in the vagueness of the word species. This is often called the species problem in modern science. But here's what we know. The presence of archaic DNA in modern humans remains a fact. It shows that these ancient lineages did not just vanish. They simply merged into the broader human population over many thousands of years. Genetic evidence shows that Neanderthals and Denisovans have distinct relationships with major populations. These groups are often described as African, European, and East Asian. Sub-Saharan African populations typically show no evidence of archaic genetic admixture. They carry almost no DNA from Neanderthals or Denisovans. In contrast, an individual with ancestry beyond Sub-Saharan Africa carries about 2% Neanderthal DNA. East Asian populations are unique because they contain both Neanderthal and Denisovan ancestry. Consequently, Denisovan genetic admixture can be used as a distinguishing marker. It identifies East Asian populations when compared to other major human groups. New research from China has provided a clearer picture of this lineage. The Harbin skull, also known as Dragon Man, is a key piece of this puzzle. This skull is at least 146,000 years old. Researchers recovered the Harbin skull in northeastern China. For a long time, its identity was a mystery. In 2025, a study used cutting-edge techniques to analyze it. They extracted mitochondrial DNA from the dental calculus present in the skull. This is calcified dental plaque. It provides a protected environment for ancient DNA. Here is the problem. Morphological studies initially suggested that Dragon Man was a new species. However, the genetic data proved otherwise. The Harbin individual clearly belongs to an early Denisovan lineage. This skull is the largest archaic human skull discovered to date. It features a massive brain size and a unique arched brow ridge. This discovery fills a major gap in the morphology of Denisovans. The Denisovan lineage is categorized into at least 3 distinct branches. Scientists label these branches as D0, D1, and D2. The D0 lineage contributed DNA to modern East Asians. The D1 lineage is preserved primarily in Melanesian populations. This distribution suggests that Denisovan populations ranged across a wide area of Asia. They lived in Siberia, Tibet, Laos, and even Taiwan. A notable discovery occurred in the Baixia Karst cave on the Tibetan plateau. A partial mandible, known as the Xiahe mandible, was found there. Ancient protein analysis linked this fossil to the Denisovans. It is more than 160,000 years old. This find confirms that Denisovans were the first humans to occupy high-altitude regions. Modern Tibetans inherited a specific gene mutation from these ancient people. It is the EPAS1 gene mutation. This mutation assists with adaptation to low oxygen levels at high elevations. It was direct inheritance from a Denisovan population. This trait allowed their descendants to thrive in the harsh environment of the Himalayas. East Asian populations also carried the MUC19 mutation. This mutation is related to mucus secretion in the eyes and mouth. It is another piece of the genetic inheritance from Denisovans. Some European populations, such as Icelanders, carry small amounts of Denisovan DNA. However, they likely inherited it indirectly. This happened through interbreeding between Neanderthals and Denisovans thousands of years ago. Keep this in mind. The genetic map of Asia is a result of multiple admixture pulses. One study identified 3 distinct waves of Denisovan introgression into modern humans. The timing of these events is difficult to pinpoint from the fossil record alone. However, we know that these ancient genes continue to function in us today. They influence our immune systems. They influence our ability to adapt to our surroundings. They are silent markers of a history that was almost forgotten.
This is What Is It? Uncovering the Unknown.
In contrast, traditional Y-chromosome haplogroups have no inherent relationship with these populations. One hypothesis suggests that haplogroups reflect historical migration patterns. They are not fixed indicators of racial classification. Paternal lineages can retain a specific Y haplogroup through many generations. Meanwhile, the descendants can become physically indistinguishable from a different majority population. This happens through consistent intermarriage over hundreds of years. For example, consider a man with Y-chromosome haplogroup O from East Asia. If he marries a woman with British ancestry, their son will carry haplogroup O. This son is of mixed East Asian and European ancestry. If this lineage continues to marry into the British population, a change occurs. After 8 generations, the descendant may appear entirely white in physical appearance, yet he will still carry haplogroup O on his Y chromosome. This illustrates that haplogroups track paternal lineage only. They do not determine the overall ancestry of an individual. They do not determine the population identity of a group. Any Y chromosome haplogroup can, in principle, be found in any population. Certain markers are more frequent in specific geographic regions. Haplogroup R is frequent in Europe. Haplogroup J is common in the Middle East and among Semitic populations. Haplogroup O is frequent in East Asia. Haplogroups C and Q are found among indigenous peoples of the Americas. Scientists use specific markers to trace these lines. These are called SNPs, from the non-recombining region of the Y chromosome. This region is known as the NRY. It makes up 95% of the Y chromosome. Because this region does not recombine, it remains stable over time. It allows researchers to trace direct paternal ancestral lines back thousands of years. Look closely at the data. Haplogroups pertain to deep ancestral origins. They date back to a time long before modern national identities. The Y chromosome is passed only from father to son. This makes it a powerful tool for genealogy. However, it represents only a small fraction of our total DNA. The human Y chromosome contains about 58 million base pairs. This is only 2% of our total genetic information. A skeptic would argue that the NRY is the most reliable tool we have. These markers provide a clear path through the fog of human migration. They are used in forensic science to identify individuals and their origins. But we must remember the limitations of this tool. Relying solely on paternal markers can ignore the majority of an individual's history. It can create an incomplete picture of who a person truly is. Here is the problem. If we use only one marker, we risk misinterpreting the history of a whole civilization. Population genetics is a game of probabilities. It is not a set of absolute labels. We must look at the whole genome to understand the true dynamics of the past. The Y chromosome tells one story, but the rest of our DNA tells many others. And that's where the trap begins. One marker, one paternal line, and people try to turn it into a whole identity. It is not scientifically valid to use haplogroup J as evidence of race. This specific marker was detected in ancient Egyptian mummies. Some use its presence to claim mummies belong to the same race as local populations. However, Y-chromosome data alone provides a potentially misleading picture. A more rigorous approach involves analyzing genome-wide ancestry. Specifically, we should examine the presence of Neanderthal and Denisovan DNA. This would offer a more meaningful basis for discussing population affinity. A significant study analyzed 90 mitochondrial genomes from Egyptian mummies. These samples were recovered from the site of Abu Sir el-Malek in Middle Egypt. The mummies span a period of 1,300 years. This timeline covers the New Kingdom, the Ptolemaic period, and the Roman period. The data reveals that ancient Egyptians shared more ancestry with Near Easterners. They were more closely related to Neolithic and Bronze Age Levantine populations. This affinity is distinct from the genetic profile of present-day Egyptians. Keep this in mind. Present-day Egyptians have received additional sub-Saharan African admixture in more recent times. This increase in African ancestry occurred predominantly within the last 2,000 years. The study estimated this influx happened roughly 24 generations ago. This corresponds to about 700 years in the past. That's an estimate, one model. It doesn't erase older, slower gene flow. The Y-chromosome haplogroups of 3 ancient individuals were identified. 2 were assigned to the Middle Eastern haplogroup, J. 1 was assigned to haplogroup E1b, 1b. This latter group is common in North Africa. This mix of markers reflects the complex connections between Egypt and the Middle East. These connections date back to prehistory. They involve commerce, diplomacy, and large-scale immigration. One example is the immigration of Canaanite populations known as the Hyksos. They entered Lower Egypt during the Middle Bronze Age. This history created an intricate genetic exchange. Foreign rule by Libyans, Persians, and Greeks also left a mark. However, the genetic time transect suggests a surprising continuity. The population of Abu Sir el-Malek remained stable during the Roman and Ptolemaic rules. Foreign conquest impacted the population only to a limited degree at the genetic level. The genetic impact of Greek and Roman immigration may have been concentrated elsewhere. It might have been more pronounced in the northwestern delta, or among the elite classes. The archaeological site of Abu Sir el-Malek provided 90 mitochondrial genomes. These samples span over 1,000 years of history. However, we must view these results with caution. This was a single local community in Middle Egypt. It does not represent the entirety of the Egyptian civilization. And social class matters too. Look at the royal families, especially during the New Kingdom, the 18th and 19th dynasties. To keep their bloodline pure, they often married within their own distinct circle. Sometimes, brother married sister, but biology has a price. This extreme inbreeding caused severe genetic disorders, creating a genetic profile completely different from the common people. So you have the royals in a bubble, and you have the rest of the country, trade routes, ports, and borderlands, pulling in different directions. It is a complex mosaic. Look closely at the methodology. The researchers measured shared genetic drift with modern humans. They focused on the Levant and the Near East, but they left a massive void in the data. No percentages for archaic DNA were ever reported. We have no data on their Neanderthal components. We have no record of Denisovan admixture. But it means this study can't answer the archaic question. The researchers left these benchmarks completely untested. This absence is a massive blind spot in the report. They tell us about modern relatives, not deep ancestors. This is a striking contrast to other recent finds. The Harbin skull was identified using rigorous protein analysis. That study used ancient evidence to reach a conclusion. They showed the dragon man was a Denisovan. That is a rigorous standard of evidence. It allows us to define populations with precision. Modern East Asians are identified by these archaic markers. They carry a unique blend of heritage. But in the Egyptian study, silence. It's not that they failed to find these markers, it's that they didn't even look. Here's the problem. This oversight creates a major technical limit. We cannot talk about population identity using only Y-chromosome haplogroups. Markers like haplogroup J only track the paternal line. They represent a tiny fraction of our total DNA. To truly understand a population, we must see the whole picture. We must see the archaic DNA percentages. This is one of the most meaningful ways to build a map. The Near Eastern affinity is a useful clue, but it is not a final answer. We're missing one of the deepest signatures in human history. So, where does this leave us? We are revisiting history, but we have to be honest about the blank pages. First, the dragon man. Is he a direct ancestor or a fascinating cousin? Some researchers still argue he is a separate species, Homo longi. The DNA points toward a Denisovan lineage. The bones say something unique. Morphology and genetics do not always agree. This remains an open case. Second, not definitive? Remember, Y haplogroups are just one thread in a massive tapestry. A population can shift its entire physical appearance while keeping a single paternal marker. Just because you carry the marker does not mean you know the whole story. It is a clue, not a conclusion. And finally, the map is incomplete. Whether it is the caves of Siberia or that single cemetery in Egypt, we are looking at the world through a keyhole. We cannot judge an entire empire by one local community. The story of humanity is not about simple lines. It is about mixture, movement, and survival. The old labels are fading, and the new map? We are just starting to draw it.
This is What Is It? Uncovering the Unknown.
Because this data set starts late. New Kingdom and after. So what would we see if we went earlier? Old Kingdom Egypt next. What happens when the next cemetery is sequenced?